a star larger than 8 times the mass of our Sun runs out of fuel, it can no longer support its own weight. The core collapses inward, crushing matter together until it violently detonates outward in a supernova. The resulting explosion is so intense, it can outshine its entire host galaxy. You are looking at a spiral structure containing roughly 100 billion stars, and a single supernova can glow brighter than all of them combined. But catching one in the act is an astronomical lottery. In a standard galaxy, you can expect on average only 2 supernovae per century. Even when we know a star is nearing the end of its life cycle, the error bars are massive. Take the red supergiant Betelgeuse in our own Milky Way. Astronomers know it will explode soon, but in cosmic terms, soon means any time in the next 100,000 years. Because of this extreme unpredictability, we almost always miss the critical breakout phase, those pristine first few hours of the blast. By the time our telescopes detect the light, the ejected material has already crashed into surrounding gas and dust, warping the explosion's original geometry. Relying entirely on this corrupted aftermath has stalled progress in 2 major fields of astronomy. Stellar physicists are missing the internal mechanics of how a core actually collapses, and cosmologists are missing crucial markers needed to measure the expansion rate of the universe. To answer these deep physical questions, we need to find a way to circumvent that timeline, catching a star in the exact moments it tears itself apart. In 2015, researchers found a workaround. By looking deep into the universe's past, they tracked the light from a dying star that exploded 9.3 billion years ago. Between Earth and that ancient supernova sat a massive galaxy cluster. The immense gravity of that cluster warped the surrounding space-time, acting like a lens and forcing the traveling light rays to bend along multiple curved paths. Because those separate paths were different lengths, the exact same explosion appeared in 4 different locations in the sky, delayed by days and weeks. But physical distance wasn't the only factor causing a delay. According to general relativity, light passing through heavily curved space-time actually appears to travel slower relative to an outside observer. This effect, known as the Shapiro time delay, is a well-tested physical law. We first proved it in the 1960s by bouncing radar signals off Venus and measuring the fractional delay caused by the Sun's gravitational field. Applying that math to the warped supernova, scientists mapped the mass distribution of the galaxy cluster and calculated exactly when a 5th image of the same explosion would emerge from a completely different path. In December 2015, they pointed their instruments at the target coordinates, and the delayed light arrived perfectly on schedule. Measuring the time delay between those distinct appearances gave astronomers an entirely independent way to calculate the Hubble constant, offering a new method to gauge how fast the universe is expanding. While that ancient light provided an elegant solution for measuring cosmic expansion, it had been traveling for billions of years. It was nowhere near pristine enough to show us the actual breakout phase of a detonating core. To see the true geometry of a star's death, we had to turn our attention back to the local universe and capture a fresh explosion in its opening hours. That opportunity arrived in April 2024. The automated Atlas survey, which constantly scans the night sky for fast-moving transients, detected a rapid brightening in a spiral galaxy. They had caught a supernova, designated 2024 GGI, within a narrow 5-8-hour window of its breakout phase. This triggered an immediate global race. Astronomers rushed to point the Very Large Telescope in Chile at the coordinates before the explosion's pristine shape crashed into the surrounding dust. To determine that shape, they used spectropolarimetry. When incoming light passes through a specialized prism, it separates based on the direction the light waves are vibrating. Measuring that polarization tells you the physical structure of the blast. Researchers tested 2 theories. If driven by neutrinos, the shape is a messy, irregularly bulging mass. If driven by magnetic jets, it expands along a clean axis, like a symmetrical football. The data eliminated the irregular mass, revealing a clear axis of symmetry that shape matches the jet-driven model. But there is a serious problem with that answer. Three-dimensional simulations consistently show that magnetic jets inside a collapsing star are highly unstable, wobbling, twisting, and kinking into chaotic lobes, lacking the stability needed to punch cleanly through a star. This contradiction forced a completely new hypothesis. What if the fatal instability of those jets is actually the trigger? As the jets violently wobble and fail, they create massive pressurized shock waves deep inside the star, which merge to drive the symmetrical explosion from the inside out. Catching this single breakout phase proved that neither of our legacy models were entirely correct. The exact mechanisms tearing these stars apart are far more complex than we thought. We no longer have to rely on a stroke of astronomical luck to study stellar death. By combining the deep-time predictive power of general relativity with the brute force speed of automated sky surveys, our capacity to observe the cosmos has shifted from passive waiting to active tracking. With a new generation of observatories coming online, capturing supernovae within the first 24 hours of detonation will soon become routine. Solving this one observational problem is bridging a massive gap in astronomy, supplying the missing data for both the microscopic mechanics of a collapsing core and the macro-level expansion of the universe itself. By finally catching the unseen moments of destruction, we are assembling a verifiable rulebook for the most extreme mechanics in the universe.